Yeah, dear students, let's see this question of electrostatics from Pathfinder. It's MCQ question number 14. The question is saying conducting a sphere of radius R1 is surrounded by a dielectric layer of outer radius R2 and dielectric constant epsilon R. If the conducting sphere is given a charge Q, determine surface density of polarization charges on the outer surface of the dielectric layer. These are the four options. We have to tell which of these are correct. So as described in the question, this is a conductor of radius R1 surrounded by a dielectric layer up to radius R2. Dielectric constant is epsilon R. Conductor is given a charge Q. Obviously, charge will reside at the outermost surface. Because of polarization, some bound charges will appear here. Suppose bound charge appear here as a minus QB, and this dielectric is neutral, so net charge has to be 0. So equal and opposite bound charge minus Q plus QB will appear at the outer surface. So we have to tell the surface charge density at the outer surface because of the polarization. So if the surface charge density here is a sigma B, so obviously sigma B will be QB divided by the area of the outer surface, that is a 4 pi R2 square. So my main job is to find QB. If I get QB, I will get sigma B. So for that thing, let me go to a general point here within the dielectric. Suppose that point P, and this point is say at a distance R from the center of the conducting sphere. So electric field here, if there was no dielectric, so electric field here would have been, say, E naught would be 1 over 4 pi epsilon naught. In the absence of dielectric, that electric field will be 1 over 4 pi epsilon naught Q by R square. If there was no electric, if there was no dielectric, there would not be any minus QB. The only charge present would be Q. That is a conductor, a spherical conductor. So to find electric field at an outside point, I will have to just put all the charge at center. So electric field here will be 1 over 4 pi epsilon naught into Q by R square. Now, from the definition of dielectric, electric field at P now, when dielectric is filled, will become epsilon R times smaller than the electric field when there was no dielectric. That is actually the definition of a dielectric constant. So electric field at P when the dielectric is there, so would be electric field in the absence of dielectric, that is E naught divided by epsilon R. So E at P is equal to, put the value of this E naught and epsilon naught. So that is a 1 over 4 pi epsilon naught. Obviously divide by epsilon R also into Q by R square. And obviously this electric field is because of all the charges present in the space. Charges present in a space are, there is this charge, there is this charge, there is this charge. All these charges at the spherical surface, so they can be treated as on the shell. We know that because of a shell, electric field inside the shell is 0. And outside the shell, to find electric field, you put all the charge at the center. So because of this plus QB, there will not be any electric field at P. So at the electric field P, that is because of Q and minus QB. So to find net electric field at P, I'll put all the charges at the center, Q and minus QB. So the same electric field that I've written here can be written as a 1 upon 4 pi epsilon naught Q minus QB by R square. Some simplifications. So this 1 over 4 pi epsilon naught and this will get cancelled. R square will get cancelled, and that is a Q divided by epsilon R is equal to Q minus QB divided by nothing. So from here, QB, I will get Q into 1 minus 1 by epsilon R. And in fact, that is a direct formula for the bound charges. So what I have to do, I have to just put the value of this QB here. So I am putting value of QB. This QB is equal to Q into, and that can be simplified as a epsilon r minus 1 divided by epsilon r. So here 4 pi epsilon r, and that is r2 square. So let me check the options, and this is what the option D is. So final answer is option D. That is the correct answer. Thank you.